Good afternoon, everyone. Today, we are very happy to have Jonathan to be our speaker today, and he will talk about the holographic Markov gap or space-time emergence at code dimension 3. So the floor is yours.
Great. Thanks so much for the introduction, and thank you for the invitation to speak. I've spoken at one of these seminars before and really enjoyed it, or maybe a slightly different seminar, but with some of you in the audience. So I'm going to be telling you today about a paper that I posted a few months ago with Patrick Hayden and Onkar Parakar. The archive identifier is here if you'd like to take a look. But it's a pretty big paper. There's a lot of detail in it. There's a lot of different kinds of calculations and insights, which makes it hard to talk about. So rather than try to tell you everything that's in the paper and burden you with a lot of details, I've decided for this talk to try to really focus on guiding you through a few of the main results from the paper, and especially focusing on some of the major insights that we've pulled out of this paper. Because of that, there's a lot of material in the paper that we aren't going to cover. So if you like to talk and you're interested, I encourage you to take a look at the paper itself, because there's plenty more to learn. The title I've chosen for the part of the paper I'm going to be telling you about today is the holographic Markov gap, or spacetime emergence at codimension 3. And I'm not going to explain what those words mean right now. Hopefully it'll become apparent over the course of the talk. But let's start by saying that the question that motivates this work, and I've written that down here, it's a question that motivates, I think, a lot of contemporary work in quantum gravity, is how do detailed features of bulk geometry emerge from boundary entanglement? So by this point in our field, I think it's pretty well understood, or pretty well believed, that in ADS-CFT or in holographic quantum gravity more generally, space-time, this sort of continuous geometry that we inhabit, is an emergent phenomenon arising from entanglement in fundamental degrees of freedom. And this is an idea that I think has been advocated really strongly by Mark van Ramstonk, and in a little bit we'll talk about his original arguments for this idea. But I would say that a lot of our understanding of this emergence is still pretty coarse. We understand the emergence of these things called quantum extremal surfaces, and we understand how they emerge from bipartite boundary entanglement, this thing called the entanglement entropy. But there's a lot more detail we might try to understand about where geometry comes from. And what we're going to be doing in today's talk is pushing a little bit at the boundary of our understanding of these more detailed features. So here's the plan of the talk. The first two sections of the talk are going to be review. I'm going to start by talking through Mark van Ramstonk's original argument for how space-time emerges from entanglement, from his paper called, I think, Building Up Space-Time with Entanglement. And the main reason I'm reviewing that, well, those of you who haven't seen it before, it's a beautiful argument and I think worth thinking about. But I'm bringing it up because I want to focus on how the existing argument focuses on a specific type of boundary entanglement that I'm going to call bipartite boundary entanglement. And from there, we'll be able to talk about a feature of bulk geometry that lets us look at more complicated entanglement structures, which is a bulk thing called an entanglement wedge cross-section. I know some of you have worked on these. I'll be reviewing what they are, and I'll be talking about this beautiful paper from Chris Akers and Pratik Roth that makes a connection between entanglement wedge cross-sections and complicated entanglement structures. From there, we'll be able to go on to the new results from our paper. And the main thing we're going to be doing in this third bullet point is we're going to be, I'm going to tell you about a sharp bound that we've proved on the geometry of these entanglement wedge cross-sections. And I'm going to give that bound an interpretation in terms of space-time emergence. And that's going to be sort of the meat of the talk. I will try to give you intuition for how we proved this result, and I'll give you a sketch of the proof. I'm going to be pretty sketchy about it because I don't think it's necessarily useful in a talk for me to give you all the technical details, but I'm going to try to convince you that it's true, and I'll tell you how we proved it. So as a final comment before I really get into the meat of the talk, I've prepared the talk to be on the shorter side because I'd like to encourage a lot of discussion. So if you want to ask any questions or make any comments, please feel free to interrupt me and unmute yourself at any point and just talk. So before I actually get into the talk, are there any questions about the plan or anything I've said so far? Okay, great. So let's talk about Mark van Ramstonk's original sort of argument. One moment. Original argument for the emergence of spacetime from entanglement. And the sort of workhorse formula in all of this work is the Riyadakinagi formula and its generalizations, which tells us, as a very, very brief review, that in ADS-CFT, or more generally, we think in any holographic theory of quantum gravity, although I'll draw it in ADS-CFT, we imagine we have some asymptotically ADS spacetime, which I'll draw as a cylinder. And on that spacetime, we single out some domain of dependence, a causal diamond A, to which we can associate a state in the boundary theory. And, if we have a state in the boundary theory, we have a spacetime in the bulk theory, and the Riyadakinagi formula tells us how the entanglement entropy of that boundary state is related to a simple geometric quantity in the bulk, which is the area of this so-called minimal surface, or minimal extremal surface, or quantum extremal surface, depending on how general you want the formula to be, plus some order 1 corrections and a small G Newton expansion. Okay, I'm assuming that this is not a surprise to anyone. This is, the big thing these days. So what Mark observed in this paper was, it started from a thought experiment, where he says, imagine we have 2 asymptotically ADS regions, which I'll draw as circles, A and B. And we have some pure state on the joint boundary system, A and B, that is represented in the bulk by some connected spacetime. Okay, and I'll draw that spacetime as some, complicated higher genus thing. Really, I'm just drawing a space-like slice of that spacetime. Okay, and what is the minimal surface for the region A or the region B? Well, it's going to be some curve like the purple one I'm drawing here that cuts this space-like geometry into a region that lives towards A and a region that lives towards B. Okay, and that's this thing we call gamma min. So what Mark observed is that if we decrease the entanglement entropy, the von Neumann entropy of the A system or the von Neumann entropy of the B system to 0, then by the Riyadakinagi formula, that implies that we are shrinking this separating surface gamma min to 0. And if we shrink those entanglement entropies all the way to 0, if we shrink this gamma min surface area all the way to 0, that implies that this geometry is at some point going to pinch off. So we're going to destroy the space-time connection. Okay. So this is one of the thought experiments that Mark offered to explain this notion of space-time emerging from entanglement, right? If we destroy all of the entanglement, we separate, we cut off the connection between these 2 spacetimes. So the specific kind of relationship that we're discussing here is a relationship between what I'll call a bipartite entanglement measure. I'll explain what that means in a moment. So we have some bipartite entanglement measure S of A, and it is related to the emergence of some codimension 2 feature of the geometry. That's this codimension 2 extremal surface gamma min. Okay. It's a very important codimension 2 extremal surface, right? It separates 2 sort of complementary regions of spacetime. And so by understanding it, we can understand how those spacetime regions are connected. But it's still a fairly coarse sort of feature of the bulk geometry, right? Knowing about one minimal surface and its area doesn't tell us very much about the actual geometry and where it comes from, okay? I also want to comment about what I mean when I say this is a bipartite entanglement measure. Well, as any quantum information theorist will tell you, what the von Neumann entropy means, what the entanglement entropy of the state tells you is how much entanglement you can distill from that state. So if Alice and Bob hold some state on the system AB, and Alice has half the state and Bob has the other half of the state, and they want to try to convert that state into some simple entangled state, they want to try to convert it into just a bunch of EPR pairs, then the von Neumann entropy, its role as a quantity is to tell them how many EPR pairs they can get from this distillation process. So that's what I mean when I say this thing encodes bipartite entanglement. It really just tells us an effective number of maximally entangled states that are shared by Alice and Bob, right? So it's a bipartite notion of how these two systems can be correlated. It doesn't tell us anything about how they might be correlated with a third system, C, for example. Okay. Any comments or questions about that? That's the first part of the talk, talking about this bipartite entanglement emergence. Okay, so now let's talk about these entanglement wedge cross sections. Now, the idea is, I just told you that this elegant and simple feature of bulk geometry, these Riyadakinagi surfaces or quantum extremal surfaces, tell us something about how space-time emerges from entanglement, but they obviously don't tell us anything. Don't tell us everything. So the natural next thing to do is to look for slightly more complicated features of the bulk geometry that are still simple enough that they might have a straightforward boundary interpretation. Okay, and one of these was offered simultaneously in these two papers that I've cited here, called an entanglement wedge cross-section. And it's actually sort of easier to tell you what an entanglement wedge cross-section is just by writing down two examples than by giving a formal definition. So for our first example, we're going to look at the state of two intervals in the vacuum of ADS3. So this circle that I'm drawing here represents a time slice of the ADS3 vacuum. Okay, so it's just a hyperbolic disk. And I look at two boundary intervals, A and B. And specifically, I choose these boundary intervals to be large enough that the minimal surface is this connected one here. This is gamma min, this surface that I've just drawn. Right, there's another potential surface, which is a minimal surface here for A and a minimal surface here for B, but I'm going to assume that that's not the true minimal surface, right? So in particular, that means we're in one of these phases where the entanglement wedge is connected, right? Where when I talk about the entanglement wedge, I mean this region that I've highlighted here. Okay. So what is the entanglement wedge cross section? Well, it's a cut of the entanglement wedge that separates the entanglement wedge into a region that is adjacent to A and a region that's adjacent to B. So that's this cut here that I've called sigma AB. And how is the entanglement wedge cross-section defined? Well, it's defined as being the minimal such cut. Okay. In particular, that means because it's minimal, it's going to meet its endpoints at right angles, which will be very important for us later. And it's a fairly simple quantity. It's defined by a minimization procedure. It's sort of an interesting constrained minimization procedure because we're minimizing over cuts that divide the entanglement wedge in a simple way. Other candidate cuts might look like this, but none of those are going to be minimal. The green curve that I've drawn is going to be the minimal one. Okay, let's do one more example, which I think will be helpful in visualizing these things, which is imagine I have some state whose space-like geometry is a three-boundary wormhole. Okay, so I have two asymptotic boundaries A and B, and some third asymptotic boundary, and I can tune the sizes of the horizons of each of these asymptotic boundaries so that the minimal surface for the region AB, that is A union B, is this geodesic here. So I'll call that gamma min. So once again, we're in a situation where the AB entanglement wedge is in a connected phase, right? It's this highlighted region here. And what's the entanglement wedge cross-section going to be? Well, it's going to be some surface that starts on gamma min, loops around the back of the wormhole, and comes back up to gamma min. And again, these intersections with gamma min are going to be right angles. Okay. So I've drawn this in two fairly simple examples, but hopefully you can understand how this simple geometric quantity would extend to an arbitrary spacetime. And obviously there are covariant generalizations like with the Riyadakinagi surfaces, where you look at, the set of such surfaces that are locally extremal and you minimize over those. It's the usual story that you're familiar with if you've ever thought about the HRT formula. Okay, so in the two papers that proposed these objects as an interesting sort of thing to study, they proposed that on the boundary, the areas of these surfaces would be related to something called entanglement of purification.
Sorry.
Yes.
I have a question here. So,
please.
Does this sigma A B has some minimal sense or extremal sense, or is?
Yeah. So it's an extremal surface. It's a segment, right? It's compact. It's not an infinitely, it's not a surface of infinite extent like a lot of the RT surfaces. But it locally satisfies, it's like a local extremum of the area, right? If I perturb it a little bit, then the area is going to increase. Okay. For example, if I look at this sigma up here, if I were to deform it out like this, that would cause a local increase in the area. Or rather, locally, it wouldn't change the area because it's extremal, and then to second order, it would cause an increase in the area. Okay. So this thing is supposed to be a global minimum among all surfaces that cut the entanglement wedge. Make sense?
Yeah. And does it have, for example, the minimal surface? You can use the conical defect to represent it in the gravity language, right?
Right.
But for the sigma AB, is there some gravitational action for that?
It's definitely more complicated. So there is, I'm going to talk about that in just a minute. Okay. So I think that'll be, there's a gravitational path integral interpretation here, which is going to be where this sort of conical defect language comes from. And I'll talk about that in just a second. Okay.
Okay, thanks.
So, like I said, the original proposal was that this thing should be dual to a boundary quantity called entanglement of purification. I'm not actually going to tell you what entanglement of purification is. It's an interesting quantity, but it's really beyond the scope of this talk because it's not going to be the dual that I'm going to be talking about. So they proposed that this quantity called the entanglement of purification, which you can go look up in any of the QI literature, is dual to the area. So to be clear, the entanglement of purification is a boundary quantity. And they proposed it was dual to the area of this cross-section divided by 4G Newton. So this, I'll just say a couple words, which is that this conjecture is very interesting. It comes from a lot of sort of intuition for how holography works that comes from tensor networks. I think it's possible that this conjecture is true, but it hasn't been established using any real gravity tools, for example, the gravitational path integral. So there's an updated proposal for the dual of these entanglement wedge cross sections from Dutta and Faulkner, which does actually use the gravitational path integral. And they propose that this quantity is dual to something called reflected entropy. This reflected entropy is denoted by SR for reflected of AB. And they say it's dual to the area of sigma AB over 2G Newton. Okay, so these two conjectures can be simultaneously true. I'll talk more about what the reflected entropy is in a second. But for the moment, all it's important to understand is that these two quantities, EP and SR, are defined in a very different way. They're completely sort of unrelated quantities. And in a generic quantum state, they're not going to have a simple relationship. Now, it's possible for both of these conjectures to be true if in holographic states they do have a simple relationship. SR is equal to twice EP. That hasn't been established, and it's sort of an interesting question that I'm not going to be talking about. But to answer your question, Dongsheng, This reflected entropy can be defined using a replica trick. And this is what Dutta and Faulkner did, this thing is defined using a replica trick. And if you look at the sort of path integral corresponding to that replica trick, and you make this assumption of replica symmetry in the gravitational saddles, and you talk about quotients, you can tell a very similar story to the Lukowitz-Maldacena story. And you can end up with something that looks like, that is analogous to their simple conical defect geometry. But I would say it's a fair bit more complicated because basically you have to do two simultaneous replications. You have to replicate around the gamma min surface and also around the sigma AB surface. So it's not as simple as just having a single conical defect. It's something more complicated where both surfaces start getting in the mix. Okay. So let me define this reflected entropy, because it's going to be, you actually won't need the definition for the rest of the talk, but I think it's a very interesting quantity. So I'm going to tell you what the definition is. And to define the reflected entropy, you start with a very simple observation, which is that if I have an operator, O, that maps a Hilbert space H to itself, well, I'm free to think of this as a vector, which I'll draw with a ket with a doubled bracket. Okay, I'm free to think this as a vector on the space of operators, right? Which is H tensor the dual space of H. So this is no surprise, right? I mean, operators form a vector space, right? And if they're operators on a Hilbert space, then there's a natural inner product on the space of operators. So I'm free to think of an operator as a vector on an extended Hilbert space. Okay. The reason this is interesting is that if I look at a density operator, rho, so I'm going to make rho a density operator, then I'm going to tell you that the vector corresponding to the square root of that operator, which again is an operator on this extended space, or is a vector on this extended space, H tensor H dual, that vector purifies rho. Meaning if I treat it as a pure state and I trace out the H star system, I'm going to get rho back. Okay. I mean, that's not so hard to see, right? I take two copies of square root of rho and I do this trace, and you could work it out, and you can see that trace just functions to multiply them together. So I multiply square root of rho by itself and I get rho back. Okay. Now, this is a way of purifying the state rho. Purifications are very important in quantum information theory. But because it's such a simple way of purifying rho, and I've done it, without making reference to any basis, I've just purified rho onto the space of operators, we call this purification the canonical purification. And the reflected entropy of a density matrix rho AB is defined as the von Neumann entropy of the canonical purification in the subsystem A star. So it's a kind of correlation between the A and B systems, but it's not visible if you stick just within the density matrix rho AB. You have to go to this canonical purification and look at the correlations between AA star and BB star. Okay, this is sort of a, if you've never seen this before, it might be kind of a confusing definition. Does anyone have any questions or any comments? Okay, so I'm going to tell you two beautiful and important facts about the reflected entropy that are going to form the basis for the rest of the talk. And the first fact, both of these were, the first fact was proved by Dutta and Faulkner in their original paper. And it's that the reflected entropy, SRAB, is always lower bounded by the mutual information. Mutual information being a very familiar quantity. to information theorists with a nice operational interpretation. And to remind you, the mutual information is S of A plus S of B minus S of AB. Okay. So that's going to be our first fact. I won't prove it for you, but it's actually very simple to prove. There's like a one-line proof in the Dutta-Faulkner paper. Okay. Now there's a fact number 2, which comes from this very elegant paper by Chris Akers and Pratik Roth, which is the following. So they said, well, okay, SR is always bigger than or equal to I. This reflected entropy is always bigger than or equal to the mutual information. But, what can we say? Like, what does it mean if they're very close or if they're very far apart? Can we learn something about the structure of a state based on whether these two quantities are close to one another or far apart from one another? And in particular, in the context of holographic states, although it's not really a holographic proof, it's just a large N proof, basically, they prove the following. Imagine you have a pure state on 3 systems, A, B, C, and we'll say it's a holographic state, okay? And imagine that it has a small amount of multipartite entanglement. So by that, I mean, we have some small parameter G Newton, right? We're looking at an expansion in G Newton, and we have some leading order, which is 1 over G Newton. And if the amount of multipartite entanglement in this state is parametrically small, is order 1 over G Newton, then they proved that SR minus I must also be order 1 over G Newton. Or sorry, is order 1 in G Newton, not order 1 over G Newton. So let me just restate that. If the state has a small amount of multipartite entanglement parametrically, then this quantity SR minus I is small parametrically, okay? So this quantity SR minus I is a witness for parametric increases in multipartite entanglement. Okay, if I get a parametrically large amount of multipartite entanglement, then I'm going to get a parametrically large difference in these two quantities. Okay, so here's where our paper comes in. We give a name to this quantity, SR minus I, and that name is the Markov gap. And that's where the title of this paper comes. Unfortunately, I'm not actually going to talk in this presentation about why we call it the Markov gap. It comes from you can look at section 2 of our paper if you're curious, where we define all of these terms. But it turns out that this quantity SR minus I is related in quantum information theory to the fidelity of something called the fidelity of a Markov recovery process. It's very interesting. I'm not going to talk about it at all today, but all you need to know for now is that I'm going to call this thing the Markov gap, and there's a reason for that. But let's talk about what we can actually say about the Markov gap in holography. Okay. So here's the part of the talk where, oh, sorry, hold on. Stand by. Hello, can you hear me again?
Yes, we can hear you.
Sorry about that. My cat turned off my Wi-Fi.
Hey,
oh, I can't hear you all. Hold on, one moment. Could someone say something? I'm not sure I'm able to hear you.
So John, I have a question. Can you hear me?
No, I'm not hearing anything. Would you pause the recording for a moment while I troubleshoot?
So I have a question. Like, do you have also an interpretation of the Markov gap? Like, if you replace SR by EOP, by the EOP?
Yes. So, not in pure quantum information theory. No. In holography, under this conjecture that EP is equal to half of SR, everything I'm about to say goes through because I'm going to make purely geometric arguments. Okay. But this simple quantum information argument comes from the fact. Well, I'll just write it for you. It comes from the fact that SR minus I can be written as this thing called a conditional mutual information. It's the mutual information of A with B star conditioned on B, which is a very simple quantity in quantum information theory. Conditional mutual informations are the things that show up in strong subadditivity. Strong subadditivity is exactly the statement that a conditional mutual information is bigger than or equal to 0.
Yeah, sure. Like we sort of like we had a paper on reflected entropy and thermal purification, and actually we sort of stumble across this inequality because it's a nice inequality because it proves that the behavior at long distances, also the behavior of reflected entropy, has to be stronger or equal to that of mutual information. And in conformal field theories, the behavior of mutual information is very constrained. So, well, that had a bearing on how the reflected entropy behaves. Yeah, okay. But I understand that you want to make geometric statements in the context of holographic states. So I just let you continue. Thanks.
Yeah, no, I mean that. I think that paper is very interesting. I might actually say some things about it at the end. But yeah, there is, there's a clear connection between these quantities. So let's talk about what the Markov gap looks like in holography. This quantity SR minus I, what's its geometric interpretation? SR has a simple geometric interpretation, so does I, so what's their difference? So I'm going to illustrate all of this in the vacuum because it's simplest, but everything I'm saying can be discussed in general states, and I'll try to indicate that as I go on. So let's draw our vacuum diagram again. We have two intervals A and B. They're sufficiently large that their minimal surface is this connected thing, gamma min. I'll call it gamma AB, actually, because I'm also going to draw the minimal surfaces for A and B, because those show up in the mutual information. And then I'm going to draw the entanglement wedge cross-section, sigma AB. Okay, so geometrically, what is SR minus I? Well, I'm going to give sort of a pictorial equation for this. What is SR? It's 1 over 4 g Newton times twice the area of the entanglement wedge cross-section. So I'm going to draw that pictorially by saying 2 times this green line that represents the area of the entanglement wedge cross-section. Okay? And then we have to subtract off the mutual information. Well, when we subtract off the mutual information, we're going to get a positive contribution from the entropy of AB, which is given by the area of this purple surface. And then we're going to get negative contributions from the entropies of A and the entropies of B. Okay. So all I've done is drawn a little pictorial equation for the areas that we're adding and subtracting. All right. But the reason I've done this is because it's going to be very helpful for me to regroup these areas in a particular way. All right. So the way we're going to regroup this is we're going to take one of these green lines and combine it with part of the purple surface. And I'm going to take the other green line and combine it with the other half of the purple surface. And then I'm going to subtract off the two blue surfaces. Okay. So this is just a reorganization of exactly the same terms that were in the equation before. Right. All I've done is I've split the purple surface into 2 halves, and I've put those in separate terms in the equation. Okay. But the reason this is a useful reorganization of the equation is that these individual terms that I've drawn parentheticals around, they're individually non-negative. And how do I know that? Right, so this is bigger than or equal to 0, and this is bigger than or equal to 0. How do I know that? Well, the blue surfaces are Riyadakinagi surfaces, right? They're defined to be minimal within their homology class. If I look at any other surface that is homologous to one of the blue surfaces, it has to have greater area. Now, this surface that I've drawn here, this surface that I'm highlighting right now, is a surface homologous to the blue surface, so it has to have larger area. Let me redraw these on my actual spacetime diagram, which I think might be helpful. So what I've done is I've kept the blue surfaces exactly the same, but I've shifted my perspective, and I've recombined this purple surface and the 2 copies of the green surface into something that looks like this. I have 2 red surfaces here. Okay. And I think it should be obvious to you that, if I look, for example, just at the left half of this diagram, then this red surface is going to have greater area than this blue surface, because the blue surface is minimal within its homology class. Okay, so that's just the statement I've drawn on the right-hand side, that the two parenthetical terms are individually non-negative. Okay. All right, so this shouldn't be so surprising to you, right? I mean, I just told you that in quantum information theory, we always know that SR minus I is non-negative. But it's interesting that in holography, we have sort of obviously that SR minus I is non-negative. And it comes from reorganizing our surfaces into the difference, a sum of two area differences, each of which we know to be non-negative, right? Now, the obvious sort of next question is, what else can we say? We've reformed this quantity SR minus I into something fairly simple, which is a sum of area differences of particular sort of preferred surfaces. There are these simple, locally extremal surfaces that have some kinks in them, right? And so we want to ask what else geometry can tell us about that area difference, and what that can tell us about the Markov gap in holography. So let me introduce a quick piece of notation from our paper. I'm going to call this surface here, let me draw that arrow a little bit bigger. This surface, I'm going to call the KRT surface. And this surface I'm going to call the RT surface. And those stand for Riyadakinagi and kinked Riyadakinagi. Okay? So the way I want you to think about this, and this is, I think, the real intuition that we developed in this paper, is that the Markov gap is fundamentally related to the difference in areas between two preferred surfaces, a KRT surface and an RT surface. Is there a question? Okay.
Can I ask a question?
Yes, please.
Because before you told us that the difference between SR and I will be of order of a finite term, right? Like the difference between these two?
No, so the statement was, thank you for asking, that's very important. So the statement was the difference of the two will be order 1 if the state has small amounts of multipartite entanglement. So you can look at a state. If I hand you any state and I ask you how much multipartite entanglement it has, then, oh, sorry, or maybe I'm misunderstanding your question. Were you talking about this, or were you just asking a question about finite versus infinite?
Yeah, so my question is the example you showed us consistent with the fact 2 that you are going to show, that you have showed?
Yes, it's consistent with fact 2 and in a very important way, which is that the way we should think about this is that if this quantity is order 1 over g Newton, that tells us that there is a lot of multipartite entanglement in the state, okay? Which is not something we would have been able to ask about otherwise. Asking whether there's multipartite entanglement in the state is a really hard question, right? So it's actually very useful for us to be able to answer that question just by looking at this Markov gap, right? So there are going to be states where SR minus I is order 1, and there are going to be states where it's order 1 over g Newton. And in the states where it's order 1 over g Newton, we have a large amount of tripartite entanglement.
Okay, so my question is, so for example, in this subtraction, right? Mm-hmm. If we want to make an order 1 quantity, that mm-hmm. means inside the bracket, we need to mm-hmm. have order of g Newton. And the question is, how does g Newton enter into the geometric quantity?
Oh, let's see. So, right. So great question. So I've set the ADS radius to 1, is the short answer to your question. So the small parameter in ADS CFT is not actually g Newton. it's g Newton over the ADS radius, right?
Yeah, that's the dimensionless quantity.
Right. So I've just set the ADS radius to 1 for convenience. But the real question here is, how big is this area difference compared to the ADS radius? Right? So let me think about how to answer this question best. Right. So I guess all I want to say is that by setting the ADS radius to 1, I've made g Newton dimensionless. So it could end up being the case that I could have an area, a difference of areas that is a dimensionless quantity that is small and is of the same size of this dimensionless quantity g Newton. That's not going to happen. Like, actually, the big point that I want to tell you is that we're going to find that in almost all cases, this thing has to be order 1 over g Newton.
Okay, maybe let's assume that this is the fact, and let's see what will happen in later. Thanks.
Okay. Cool. So, right. So the obvious question, is what can we say about these area differences? And I'm going to tell you that something very simple happens, which is the following. Now, this is a claim that we can prove using simple geometric techniques in ADS3 gravity. So I'm looking at asymptotically ADS3 spacetimes that have no matter in them. All right. We only did the mechanics of the proof for time symmetric spacetimes, but I don't actually really think that matters. It makes the proof a little bit simpler, but I think pretty much everything we did could be extended very simply to non-time symmetric spacetimes, if that's something that worries you. So here's the statement that we proved, okay? We proved that for any KRT surface and the corresponding RT surface, the difference in area is lower bounded by log 2 times the number of kinks in the surface, in the KRT surface. And if you want, we could restore the ADS radius here, which would work out all of these sort of confusing issues about what happens when g Newton is dimensionless. Okay. So this is an interesting inequality, because it tells us that whenever KRT has a kink in it, even one kink, its area is going to exceed the area of the corresponding RT surface by something that is of order the ADS radius, which is significant. Okay. So if we put this back into our Markov gap to get an inequality on the Markov gap, well, the Markov gap was 1 over 4g Newton times the sum of differences between KRT and RT surfaces. And if you just put it back in, you find that this tells us that SR minus I is greater than or equal to log 2 over g Newton times the number of cross-section boundaries. What do I mean by the number of cross-section boundaries? Well, if you look at this simple example I sketched up here, this surface, which is the entanglement wedge cross-section, has 2 boundaries, right? Those are those 2 green dots. I'll draw them a little larger to really emphasize this. This is a single segment, so it has 2 boundaries. But you can have entanglement wedge cross-sections that are, in more complicated spacetimes that have much more complicated topologies. You could have ones with no boundaries. You could have ones that are just closed loops, so those would have no boundaries. You could have ones that are made up of many different segments. They have a lot of boundaries, okay? And this is the inequality, and it follows, this first inequality that I've claimed immediately implies the second. And it's just because, well, every boundary in the cross-section gives a kink to each KRT surface, right? Let's look at that here, right? This boundary in the cross-section, this top boundary in the cross-section, becomes one kink in each of the KRT surfaces. And then the bottom boundary becomes one kink in each of the KRT surfaces. Okay, so that's where this funny factor of 2 comes from. Okay, so I'm going to tell you a sketch of the proof of this inequality momentarily, but what does this inequality tell us? I think it tells us something really interesting if we just stare at it for a second. And I think this gets at the interesting question that Dongsheng asked. Akers and Rath taught us that if SR minus I, if this Markov gap is order 1 over G Newton, then there must be a large amount of tripartite entanglement, right? Because they said if a state has very little, if it has parametrically small multipartite entanglement, then the Markov gap must be parametrically small. So conversely, if the Markov gap is parametrically large, then there's a parametrically large amount of multipartite entanglement. Okay? This inequality gives us a very sharp condition for when there is a parametrically large Markov gap, right? If the cross-section has a single boundary, then we know that there has to be, it's just a simple topological feature. The cross-section has a single boundary that tells us that this Markov gap is parametrically large in 1 over G Newton. Okay? And that tells us by Akers and Rath that there's a parametrically large amount of multipartite entanglement. So what I want to tell you, and this is the real meat of the talk, is this next sentence, is that these cross-section boundaries must emerge from multipartite entanglement. Because we can't have them without having multipartite entanglement on the boundary. That's what the Akers and Rath result tells us. If we don't have any of these, well, if we have one of these boundaries, then we have to have a large amount of multipartite entanglement. And the fact that this inequality scales with the number of those boundaries is interesting. It suggests to us heuristically that maybe, sort of the amount of multipartite entanglement will also scale with the number of these boundaries, that with every boundary we add to the entanglement wedge cross-section, we're going to have more and more multipartite entanglement. So that's why I called this talk Spacetime Emergence at Codimension 3. Because these entanglement wedge cross-section boundaries are codimension 3 features of the geometry. And in ADS3, at least, we can show that they require multipartite entanglement, okay? So I think we're seeing something very interesting here, which is we're seeing a higher codimension feature of the geometry, a codimension 3 feature, emerging from multipartite entanglement structure. Any questions about that? That's like the money line of the talk. Everything else is just semantics.
Yeah, I do have a question myself. So, like, isn't the number of the kinks sort of limited that you can have? Like here you have, I don't know, like 2 or 4. I'm not sure.
Yeah, here we have 4 kinks and 2 cross-section boundaries, but you can have topologies that have actually very complicated numbers of kinks. I think I drew one down here. Like, yeah, here, let me just draw a different one. So imagine I have some, I can have some complicated.
Did you feed your cat, or you forgot?
They don't eat for another hour. They're just very noisy. So I can have some geometry that has like think of some like.
Oh, like you're thinking about multi-boundary wormhole.
Yeah. Think about a lot of boundaries and a lot of holes. So this is something that's very high genus, right? The entanglement wedge cross-section could be something that is like one kinked loop around each of these higher genus holes, right? Okay, so you can have a lot of these. You can only have one of them in this very simple vacuum example, but you can have arbitrary geometries with a lot of kinks.
But if you think about like, well, I mean, if you think of geometries with a single boundary, probably like this number is going to be rather low, like you have. But indeed, like if you increase the number of boundaries and have higher topologies, yeah, I agree. Okay.
I think you can actually get an arbitrary number of kinks with a single boundary just by taking a lot of intervals.
A lot of intervals, okay.
Right. If I take A and B each to be n intervals, and I arrange them to be in some complicated connected phase, I think you can get a lot of kinks that way. But I haven't actually drawn any of these examples.
Yeah, because you want to think about like many intervals as like one subregion. Like, I see.
Right.
Yeah.
Exactly.
Like what I had in mind was much too simpler. Yeah, you're right. Like I can see what you're saying. Yeah, thanks.
Yeah, this is the problem, right? Like everything is so easy to explain in the vacuum, but it might lead you to think that things are simpler than they are. The proof works for any geometry, even ones that are much more complicated. Any other questions about this? Okay, so let me give you the sketch of the proof and then we'll be done.
So, sorry,
Yes.
like another question from Ghent.
Yeah.
So, I mean, can you localize on a particular kink in some clever way, or like the quantity that you're computing, like this Markov gap, like I mean, like it gives you like the sum over all of them, right? But like you can localize on a particular one, or
you can actually, well, you can't localize on a particular kink, but well, it's cute. You'll see it in the proof. The proof involves a sum over one factor of log 2 over 2g Newton associated to each kink. So it's sort of, you can't localize, you can't say anything about each individual kink, but there is sort of a charming way that the proof ends up giving an equal contribution from each kink.
I see.
So let me just show you that and you'll see how it works.
Yeah, thanks.
So the idea of the proof, so we're working in time symmetric states, which means that we're really doing an exercise in two-dimensional hyperbolic geometry, right? These, everything, you know, we're looking at space-like geometries that are two-dimensional and that are locally hyperbolic. And what I'm going to tell you is that the KRT and the RT surfaces, well, they're both geodesics. The KRT surface isn't a geodesic everywhere. It's made up of geodesic segments that meet at kinks, but these are both local geodesics that bound some hyperbolic 2 manifold. So let's look at through 4 examples I've drawn here. The first one is the KRT and RT setup that we just talked about in the vacuum. They bound some simple hyperbolic 2 manifold, which is just this, you know, this membrane that stretches between those 2 surfaces. Okay, it's a subregion of the Poincare disk. We could also imagine something that looks like this second example, which is probably the typical one that you should keep in mind. We have some, this is like some portion of a wormhole geometry that has a hole in it, you know, it's some higher genus wormhole geometry. And we have one closed loop on the left, that is the RT surface, and one closed loop on the right, that is the KRT surface, and the KRT surface is kinked, right? So this kind of thing can arise in a generic geometry, okay? We can imagine having something, I don't know if we can actually have this based sort of on Michal's comment, but you can imagine having something sort of like this, where you have like 2 intervals, you know, two sort of, you have an RT surface that is made up of 2 segments, and a KRT surface that's made up of 2 segments, each of which has a lot of kinks, and they link each other in some complicated way. Okay. And as a final example, you can imagine a case where you have, say, a couple of RT surfaces, which are, say, closed loops on some wormhole geometry, and a couple of KRT surfaces. And the reason I've drawn this one is because I just want to emphasize to you that the KRT surface doesn't have to have kinks, right? It's made up of the entanglement wedge cross-section. And because the entanglement wedge cross-section has, you know, the entanglement wedge cross-section can have pieces that have no boundary. It can have closed loops. And that's what this closed loop here is. Right? It's some portion of the entanglement wedge cross-section that doesn't have any boundary. Maybe it'd be helpful if I drew a quick example, actually. The easiest example is in a, will this be easy? Yeah, let's look at a 4-boundary wormhole really quick. Okay, so here's A, B, C, D. And I'm going to engineer my 4-boundary wormhole so that the throats between the AC and BD are very small. So we should imagine that gamma min is this surface. Okay, so that's the minimal surface for AB. It separates the AB region from the CD region. In this case, what's the entanglement wedge cross section? It's this closed loop here. Okay. So in this case, what's the KRT surface going to be? It's just going to be the entanglement wedge cross section. It's just going to be some closed loop. Well, I guess the KRT surface is going to be the union of these 2 loops, right? And the RT surface is going to be some loop over here. Okay, so I only want to emphasize to you that these, these things, these KRT surfaces might be something quite complicated. They'll have a finite number of components, but those components, some of them could be smooth loops, some of them could be kinked loops, some of them could be kinked sort of asymptotic geodesics, some could be smooth asymptotic geodesics. They're things that generically could be quite complex. Okay. So what's the idea of the proof? Well, it's very simple, and I think it's I think it's very elegant, which is the following. We look at each component of the KRT surface one by one, and we look at all of the components with kinks in them, and we perform some homotopy. And I'll draw a picture of this in a moment. So we're going to homotope each kinked geodesic to a smooth geodesic. Let me emphasize what I mean by that by redrawing my second example from up above. So I had some sort of higher genus topology with a kinked geodesic on one end. And I'm going to perform some homotopy. The work of the proof is in showing that such a homotopy exists. I'm going to perform some homotopy that deforms that red geodesic, or that kinked red geodesic, into a smooth one, which I've drawn here. And I'll draw in a dotted line where the kinked geodesic was. Okay? So on this picture, it's very simple, right? You have to verify that such a geodesic exists and that you can always do this homotopy in a simple way. But the idea is that you do this homotopy, and then you show that when you do this homotopy, you lose an area greater than or equal to log 2 times the number of kinks. And what does this give you? Well, it immediately gives you what you want, because I can write the area difference of the kinked red surface minus the smooth blue surface as being equal to, I can just add and subtract this green surface. So let me do that. Okay. And then I've just claimed to you that this first term has to be bigger than or equal to log 2 times the number of kinks. And that follows from this homotopy argument that I'll tell you a little bit about how it works in a moment. And as for the second term, well, that just has to be bigger than or equal to 0 because the blue surface was assumed to be minimal in its homology class. And the green surface I've drawn is clearly homologous to the blue surface. Okay.
Yeah, a quick question.
Yes, please.
I just want to know, where does this log 2 come from?
Yeah, I'll tell you. I'll tell you in the very next section, okay? It comes from, it's a universal coefficient in hyperbolic geometry. Okay, I'll tell you where it comes from. It's the leading term in the large argument expansion of the arc-cinch function. That's just, it's a feature of hyperbolic geometry. You have arc-cinch of x, and you take x large, a log 2 shows up. That's all there is to it. Okay?
Okay.
So the way this proof works is that you lift to the universal cover. This is going to be really sketchy. You lift to the universal cover. So you use the fact, is a beautiful fact in hyperbolic geometry, that any hyperbolic 2 manifold is universally covered by the Poincare disk. So here I've zoomed in on a little neighborhood of that kinked geodesic. And if I lift that geodesic to the Poincare disk, I end up with some infinite, kinked geodesic in the Poincare disk. And then there's some work to show that, there's going to be some unique geodesic in the Poincare disk that connects the endpoints of that lift. And then you do the homotopy in the Poincare disk. And you show that all of the right properties are kept under the universal cover. So the interesting feature of this calculation is that, well, you want to show in the Poincare disk that the red curve has bigger area than the green curve by a factor of log2 times the number of kinks. Well, where does that come from? What you do is for each segment of this red curve, you draw a geodesic to the green curve. And what happens when you do that? You create a tiling of this homotopy region by right-angled pentagons. So each kink ends up embedded as a vertex in these right-angled pentagons. All of the sides of these pentagons are geodesic. These are truly pentagons in the hyperbolic geometry sense. And then you use this sort of interesting identity from like hyperbolic trigonometry, which tells you that if you have two adjacent sides of a hyperbolic right-angled pentagon and you subtract the area of the non-adjacent side, that's lower bounded by log2. And it comes from a trig identity having to do with, sinh and cosh and arc-sinh and arc-cosh, and their large argument expansions. And that's where this log2 comes from. It's not obvious. I'd say just look at the paper for it, but it comes from hyperbolic trig identities. Okay. Okay, so that's the proof. It's look at the paper if you want the details. I don't think it's going to be a very productive thing for us to try to talk about all of the details right now. I've gone 5 minutes over, so let me just write down some open questions and then I'll thank you for your attention. So I think a really good question to ask, and probably the most pressing one, is what happens in higher dimensions? So everything we did was in ADS3. And the reason that, one reason that ADS3 is kind of special is that codimension 3 objects are just points, right? So they're fairly simple objects. If we were to upgrade to higher dimensions, we might wonder if, the boundary of an entanglement wedge cross-section is now going to be some codimension 3 surface, which might be some extensive object in higher dimensions. We might wonder if our bound generalizes, right? So as a first guess, we might imagine that the Markov gap is lower bounded by some constant, which in our case was log2 over 2g Newton, times the codimension 3 volume of the cross-section boundary. So in 3 dimensions, the volume of a codimension 3 object is just its cardinality, right? It's a count of the number of points. So in higher dimensions, we might imagine that we'd get something interesting like a volume of that cross-section boundary. That would be really cool. It would tell us something very intricate about how codimension 3 geometry emerges from entanglement in higher dimensions. But we don't have anything along those lines yet. I think another interesting question, and this is the last thing I'll write, is what happens when we add matter? Everything we did was in the vacuum, and some very interesting things could happen if we add matter to our spacetimes. Now, in the paper, I'll just say we did some perturbative calculations that indicated to us that this bound should hold perturbatively if we add a small amount of matter. But we don't know what happens for generic matter configurations. And I think it's an interesting question to ask. Okay, thank you for your attention. Sorry for my noisy cat at the end of it. I really appreciate it. And I'm happy to answer any questions that you have.
Thanks a lot for the nice talk, Jonathan. Yeah, I think we can still take some questions.
Yeah.
Yeah, maybe I could still ask some questions.
Yeah, for sure.
Yeah, I just want to know, so when you write this large or equal sign to something, like, I think probably you have also something in mind that when this equality will get saturated, meaning that SR equals to
Yes.
I in some cases.
Well, not SR equals to I, but SR equals to I plus this minimal contribution, right? These log2 times the number of kinks.
But for example, is there anything any geometry or any case that has 0 kinks?
Yes. Yeah, there absolutely is. They're all very trivial. Well, I mean, actually, there's a non-trivial geometry, which is this. I think I erased it actually. This 4-boundary wormhole I drew. Let me draw it again. This 4-boundary wormhole.
Right, exactly. I see.
Right. So in this case, where the entanglement wedge cross-section for AB is this closed surface here, you actually can tune it. You can tune the parameters of the wormhole so that SR is exactly equal to I. Okay? And what happens in that case? Well, what happens in that case is that you end up being, I think that example, I haven't done this calculation in a while, but I think that example is one where you're at a phase transition, where the area of the blue surface is exactly equal to, yeah, it would have to be, right? The area of the blue surface is exactly equal to the area of the red surface plus the area of the purple surface, right? So this is what we would call a phase transition in the Riyadakinagi formula, where there are 2 candidate minimal surfaces for A that have exactly the same area. So those are the kinds of very special edge cases where you have SR equals to I. Okay, give me 1 second, sorry. Hello. Yeah, so those are the special cases that we have in mind. That's really the only case where you can have this exact saturation.
I see. Yeah, it's still a bit confusing here actually, because if there's no kink happening, I would think no matter if there is I would think this equality always held.
No, so imagine. So remember the in fact, the KRT minus IT is exactly the difference here, right? KRT minus RT is red plus purple minus blue.
Okay, I think you're right. I think you're right.
So I can tune the moduli so that if the blue surface is truly minimal, if it's the dominant minimal surface, then I can tune this so that SR minus I is anything I want, right? In particular, I can make it 2. You know, I can make it something of order. I can make it equal to G Newton.
Yeah, I agree with you.
Yeah.
Anyone else would like to ask further questions? If not, let's thank Jonathan again. And,
thank you very much for having me.
Thank you very much. I will stop the recording now.